Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem. Check if number is a sum of power of threes. Very, very nice problem, at least in my opinion. I really like it. Short and sweet problem description, very clear examples. The solution is actually very easy to code up. Not necessarily trivial to understand it, but at least we get to spend our time doing interesting things, actually like thinking about a problem. So I'll be showing you two solutions to this one. One is kind of a more traditional solution involving like a brute force or more backtracking approach. And the second one is a bit more math or theory involved. To be honest, I thought this was just a backtracking problem, so I just coded up this one. I thought that's the one I was going to be recording for this video, and then I quickly looked at the other solutions, and it turned out there actually was a more optimal one, and as soon as I saw it, it made complete sense to me. So I hope it'll make sense to you by the end of this video. We're just given a number, let's say n equals 12. We want to know if this number can be represented as a sum of powers of 3, and they have to be distinct. So what do they mean by power of 3? Well, you have a number, 3 in this case, and we raise it to some power x. So we could start at 0. 3 to the power of 0 is 1. Any number to the power of 0 is 1. That's kind of like a base case. And then we have 3 to the power of 1. That's also very simple. It's just the number itself. And then things get more interesting. Then we have 3 to the power of 2. That's just taking 3 and multiplying it by 3. So that's just going to be 9 in this case. Then we can just kind of keep going. We get 3 again. And then 3 to the power of 3 is going to be 27. So what we want to know is if there's some combination of these powers where, let's say, maybe we include this one, or maybe we skip this one, and then we include this one, and then we include this one, and then we take the sum of the ones that we did choose, in this case, 3 plus 9, and we arrive at this number that we were given. Again, we can only use each of these a single time if we use it at all. We can also skip the powers of 3. And obviously, there's an unlimited amount of powers of 3. There's an infinite amount. So we have to kind of know where a stopping point is going to be. And I think it's pretty trivial from this example to recognize that at some point, a power of 3 is going to be bigger than the original integer itself. And at that point, we can probably stop. Like, I guess we would have calculated this one, and then we'd see, okay, there's no reason to really compute any of the other powers of 3. None of them are going to help us in this situation. So this actually is enough intuition, in my opinion, to arrive at the backtracking solution, provided you do know how to implement backtracking. It's a pattern we've been practicing over the last several days, but again, if this is not familiar to you, this is going to be a difficult problem. You can check out Leetcode.io for some resources or courses to really get good at this stuff. So now let's solve the problem knowing this. So we're going to solve this recursively, and for each power of 3, we want to consider it. How are we going to consider it? Well, I'm going to have a parameter which I'm going to call I, and that's going to tell me which power we are currently considering, right? So for I equals 0, we could include it, meaning then our current sum would become 3. Originally, let's say our current sum starts at 0, and then it becomes 3, or we could skip it, meaning our current sum stays 0. Of course, at this point, we are at the I equals 1 choice, and so here we could like include, sorry, I think I messed up, but maybe it's a good mess up. So 3 to the power of 0 is going to be 1. So that's kind of the choice here. So I screwed that up a bit, but okay, we have 1 on this side. We started with 0. And then here we didn't get the 1, so we stayed at 0. Now here we have the choice over here because we are at I equals 1. So we can either add 3 to the power of 1, which would give us a sum of 3, or we could skip it, staying as 0. I'm mainly going to explore the path that actually leads us to the solution. So on this side, we are at the I equals 2 choice. So that's what this level of the tree tells us. And so our choice is to add or skip 9. So here we add 9. We arrive at 12. I think that's very easy to recognize that this is the solution. Once our current sum, of course, equals the target number n, we can then return true. We just want to know if it's possible or not. So this is an example where we actually can find the solution. Now, let me kind of explore this path just to kind of show you what that might look like. So here we could have added 3, giving us 4. We could have skipped 3, staying at 1. From here, we could have then added 9, giving us 10, or of course we could have skipped it, staying at 1. Now we're getting close to n. along this path, but then we find that, okay, now our choice is 27. So you add that, we get to 37. You could skip that too, and then you could get to 10 here. And you might think, well, it's still possible for us along this path to reach 12, but actually, no, it's not. We have to somehow be able to detect that it's not possible, because we know that now our sums are always going to be larger than the original number itself. So we should not keep going down this path. We have to stop. Otherwise, we're just going to go infinitely deep. We do not want to do that. It's obvious here why we can't keep going. The current sum is already bigger than n. So the comparisons that we'll use in our code is, of course, like, let's say current sum is greater than n. That's going to be the simple one. The other one is going to be maybe 3 to the power of I is greater than n. And at that point, we can also stop. This is very, very important, specifically for the case that maybe it's not possible for us to form the number. Consider if our example, instead of being 12, was actually 13. It's not possible to sum up to 13 with powers of 3. And if we do not have the case where we check 3 to the power of I is greater than n, then we're just going to keep going infinitely deep. We will never stop. So this is the backtracking solution. Let's try to analyze the time complexity. It looks like it's exponential, right? We have two branches, 2 to the power of, you could say n, but I'm not going to use n because it's already used here. So let's say you could call it x. But what exactly is x in this case? Well, we know that there could be some amount of levels in this tree. That's what x really represents, but it's not going to be n. Like if n is 12 or 13, we're not going to have 13 levels in the tree. That would be way too many. That would mean like 3 to the power of 13. That is huge. We are really only looking for the number 3 to the power of I, where it's either equal to n or greater than equal to n. So let's just say like approximately equal to n. So then we can just do a bit of math. We can take the log of both sides, and specifically the log base 3 of both sides, and then you kind of simplify the math, do the algebra, you'll get I equals log base 3 of n, and you recognize that I represents the number of levels in the tree, so you can put that here, 2 to the power of log base 3 of n. Now, if this was log base 2 of n, we could simplify this down to n, so it's not in this case, it's log base 3, but you have to recognize that log base 3 is actually a smaller number than log base 2. So based on that logic, we can say that this is actually bounded. It's kind of messy here. I wish I could get rid of this line. But we can say that this is bounded by O of n. So that was a bit of math to explain this. If you didn't follow all of that, it's probably not a huge deal. I don't think you're going to be asked to go through like this process in your interview, but I'm sure you can see why understanding things like this could be useful for solving interview problems or other things. Anyways, let's code this solution up, which is pretty much a linear time solution in terms of n. So I'm going to define my function backtrack. I'm going to pass in two parameters, I, which tells us the current power, and of course the current sum, so that we can check if current is equal to n, go ahead and return true. It's usually better to put this case before the other one. Sometimes it doesn't matter, but in this case, it actually does. In my case, the other base case is going to be this. If current is bigger than n, of course, we would stop in that case. And of course, we would want to return false. But there's one other case we want to return false because we don't want infinite recursion. In the event that there isn't a valid solution, in the event that we never return true, we want to return false in this case where 3 to the power of I has already exceeded n. Now, if that's not the case, then we can take this power and then try to add it. We can try the recursion. And before I do that, let me just show you how we're going to be calling our backtrack function. We're going to start, of course, at power 0, and our current sum is initially 0. We want to return the result of this function call. And now in the recursion, there's two cases. Either we include or we skip. I'll do this include case first, but I don't think it really matters which one you do first. I'll call backtrack, and we will move to the next power, I plus 1. And for us to ensure that we've included the current power, we can just take the current sum, add to it the current power, which is 3 to the power of I. So we can just return this if it's true. So let's say if this is true, let's return true. If it's not true, then we have to keep going. We have to keep doing the brute force. Let's try the other choice that we can make, which is skipping. So backtrack, I plus 1, and the current sum stays the same. Now, if this is true, we return true, otherwise we return false. We could handle that with an if statement, but it's easier just to return the result of this function call. So I believe this is the entire code, unless I have like a typo or something. So let's try to run it. Yes, and as you can see here, it works and it's pretty efficient. But there's actually a more efficient solution. And it's possible that you can arrive at that solution on your own. I'm going to try to give you some hints right now, and then I'll just walk you through the solution. So let me kind of give you just a tiny bit of math background. It's going to be a little bit similar to what we've kind of drawn over here, but let's actually consider powers of 2 for a second, because this property also holds with powers of 2, just as it does with powers of 3. And it's somewhat reminiscent of binary trees. Consider this. We have like 1 square here. And then I double it, and then I have like 2 squares. I'm kind of drawing this in the shape of a binary tree, and then I have 4 squares. And then I just keep going. I double every single time. So I can't really easily draw this, but imagine that. I have 1, I have 2, I have 4, I have 8, and I just keep going. The property to pay attention to is this. The last term is greater than all of the previous terms combined. The sum of all of these is 7, and this is 8. It's bigger than everything that came before it. And this is sort of like a recursive property. I don't know if I'm using that word correctly, but in terms of like these sub problems, it just keeps going. Like if you take this 4, it's bigger than all the previous values combined. If you take 2, it's bigger than everything else combined. Now I could explain to you why that is. I'll take like maybe 20 seconds to do that. Like I said, my intuition is that it feels like a recursive property. Take 2, for example. It's bigger than everything previously combined, right? So if 2 was bigger than everything combined, and then we took 2 and doubled it, right? So now I have 4, and 4 could be represented as this, 2 plus 2. So my 2 accounted for the previous number, and that previous number was already greater than everything combined, and now I have an extra 2. So my extra 2 accounts for everything that came before it. So this tells me that this 2 kind of negated this 2 over here, and now I have a 2 that tells me it's greater than everything that came before it. So that's why it keeps going. It's sort of like a recursive property the way I think of it. So 8, for example, could be represented as 4 plus 4. 1 4 negates this, and the other 4 tells us it's greater than everything else combined because this 4 was already greater than everything else combined. So anyways, that holds for powers of 2. It also holds for powers of 3 because powers of 3 actually grow even more quickly. You can see it's actually even more true in this case. 27 is more than everything else combined and more so. Okay, but how exactly does that help us solve the problem? Well, let me just give you a hint. Greedy. I'll show you how it's going to work on this really, really simple example, but then I'll show you how it's going to work on a more complicated example as well. So here's how it's going to work. Let's say this is the example. What I'm going to do is I'm going to have my I, let's say, start at 0. So this is the power that we're currently at. We're going to find the largest power of 3. So let's say 3 to the I, that is still less than or equal to n, which is 12. So in this case, this would be our stopping point. I think it's obvious why we're doing this. Of course, none of these guys are ever going to help us arrive at the result if a result ever exists. And also, now this is the part where the last minute that I was talking about, the last like 2 or 3 minutes that I was talking about is going to come up. With these remaining powers, if we are trying to sum up to the number 12, these are all the powers that are less than 12. You tell me, is there ever going to be a solution where we do not include the largest power? Because we know that all these powers combined will never equal 9. They will always be less than 9. So let's just say we have 2 numbers. One is 9 and the other number is less than 9. If I want to sum up to 12, if there's even a possibility that I sum up to 12, I have no choice but to include this number for reasons like that I talked about earlier with the math. So I just have no choice. I have to include this number. And also we have to recognize we can only include this number a single time. So now this is how the greedy solution is going to work. I'm going to get to this point. So I'm going to have my I get all the way to 2. So it's here. So what I'm going to say is now my n is 12. I'm going to take this power. It is less than or equal to this. So now I'm going to take 9 and remove it from n. Now it's equal to 3. So now things are going to get a bit more interesting because now it's actually possible that there might have been like a power of 3 here that is actually greater than our current number. Like imagine instead of this being a 12, had this been a 10, we would have removed 9 from it and we would have ended up with just a 1. And we see here that 3 is actually bigger than 1. So we could actually skip this one. Okay, so now sticking with this example 12, so now we have 3. Now we see the next power. We're down to 1 now. We decremented our I. So now we're here. This is less than or equal to that. So again, anytime it's less than or equal to n, we have to include it. So we include it. So we take 3 and subtract it from that. We end up with 0. And that's how you know you can stop and return true. How would you know if you could return false, though? How would you know if there's not a possibility? Well, I think it's pretty obvious. I mean, there are multiple ways to do it, but I think one way is pretty obvious. The most obvious one is we literally go through all these powers and we still have something left over. It never equaled 0. It would never become negative because we're never going to remove a sum that's bigger than the number itself. But if it's still non-zero, that's how we would return false. Let's quickly run through an example like that one. Let me make this 82, or no, let's say 92. Now I would have my I. I'm going to keep incrementing my I until we get to the largest power that is bigger than this. So then we would end up stopping here. And then we would go in reverse order. So now we're at 4. Now we're going to work backwards. We see the current power is less than this. So subtract 81 from 92. We are left with 11. So now this is the sub problem. Now we keep going. We decremented our I. We're down to 3. Now we are here. This number is bigger though. So we skip it. So don't include this one. Now we're here. This is less than that. And I would set this to 2 now. So then we subtract that from here. Now we're left with 2. And then we decrement this. We're now at 1. We're at this power. This is bigger than 2. So we would have to actually skip this one. And now we're here. This is less than 2. So yes, we can subtract 3 to the power of 0 from 2. But we are then left with 1. So we went through all the powers. And there's nowhere left for us to go. I will probably be -1 at this point. And we still have a non-zero value. So we have to return false in this case. I hope this solution made sense to you, and I hope that you can recognize that this is more efficient because we're just going through however many powers of 3 are going to be less than n. And the math that I showed earlier will show that the time complexity of this approach will be log base 3 of n, which is definitely more efficient than n, and it's actually not even close. This is so much more efficient than n, and the space complexity is still constant. Let's code it up. Okay, so there's 2 main phases to this algorithm. I'm going to have my I equals 0. This is the power. This is the phase where we are finding the largest power of 3 such that 3 to the power of I is less than or equal to n. Then we'll just kind of keep doing this. So 3, first, I guess naively, you might code it up this way. 3 to the power of I, while that is less than or equal to n, then take I and increment it. But you have to recognize that maybe 3 to the power of I was equal to n in this case. And then we took I and incremented it 1 more time. So with this current code, what we would have to do after all of that is actually decrement I by 1 to then make sure that 3 to the power of I is less than this. Because when this loop stops, that condition is actually no longer true. So you could do it this way, or you could just put the -1 here. You could say 3 to the power of I plus 1. I know that might seem like backwards, but this ensures that then 3 to the power of I, after we've incremented it, is actually still less than n. I hope that makes sense. If it doesn't, perhaps you can code it up a different way, because there's probably multiple ways to do this. And now is the second phase where we are going to be greedy and remove the largest powers available. So we're going to do this while I is greater than or equal to 0, and we're going to compute the power. I don't want to have to do the power multiple times, so that's why I'm just putting it in a variable, but I don't think this really makes a big difference. So 3 to the power of I, if the power is less than or equal to n, just subtract it. Subtract it from n and do this. And then make sure to increment or decrement I regardless of whether we did this. Whether we include it or we skip it, doesn't matter. We need to decrement this number. After that's done, we've gone through all the powers of 3, and then at the end, we could do this. If n is equal to 0, return true, otherwise return false. So we could just return the condition itself. Now, technically, we could have put an early stop in this loop. I will kind of leave that as an exercise to you if you want to answer how we could have done that in the comments. I think the editorial actually did that as well. That is like a minor optimization, but I don't think it's a huge deal. So I'm just going to run this now. And you can see here on the left, it is efficient. I guess if I put the early stop, maybe we would have gotten that extra 1 millisecond. Actually, let me just go ahead and do that. After we've removed the current power, if n is still bigger than the current power, then we know we can return false immediately. So we can do this. If power is still less than n, that means all the previous or all the smaller powers combined are still going to be less than n. Thus, we're never going to be able to get n down to 0. So we can just return false. Now I run this, and now we did get that 100%. So even though that green feels good, I really don't think it made a huge difference. I don't think this really increases your chances much of passing an actual interview, but still fun nonetheless. If you found this helpful, check out Leetcode.io for more. Thanks for watching, and I'll see you soon.